what our next unit is up to is the subject of light. You know, we went over different types of waves before, and we looked at mechanical waves before. Now we're going to look at electromagnetic waves. And if you have them, there's some 6 colors here that, you know, if you're a Technicolor kind of person, you got red, green, blue, yellow, cyan, and magenta, kind of a purplish. It'll help you later on as we start mixing colors and get into the electromagnetic spectrum a little bit more. So what are we looking at? EM spectrum, types of radiation that travel in waves. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. You know, you have probably had some of these in chemistry last year, and this is what we're looking at. The entire electromagnetic spectrum, okay? And then this is a breakdown here of visible light here in the middle, right? You have radio waves, we got low frequency, we got long wavelength. Over on the other end, as we go from ultraviolet, X-rays, and gamma rays, we got high frequency, short wavelength, okay? The other things that are important here that we can look at is this side over here has very low energy. This side over here has very high energy, okay? The low energy radio waves and microwaves, this is just like it's in a microwave oven. That energy goes into the moisture in your food and kind of cooks it that way. Higher energy over here, these basically can make you sick and make you very, very ill. Ultraviolet rays from the sun, UV light, that's causes skin cancers and things like that. So the light-haired, light-eyed people, right? Watch out. Wear your sunscreen. Your mom was right. We got X-rays, right? Sees through the skin, bounces off the bone so you can see bone fractures. And then we have gamma rays. This is basically highly radioactive, high frequency, short wavelength, very high energy, okay? For visible light, we're looking at wavelengths of 400 nanometers to about 700 nanometers. The longest wavelengths are red. The shortest wavelengths are violet. And I don't know if you used Bunsen burners back in chemistry, but what color did you want your flame? You wanted your flame in here in the violet range because the violet range has a shorter wavelength and a higher energy. Light and the electromagnetic waves do not require a medium. Okay, they can pretty much sail through whatever. Okay, the speed of light though depends on the medium. Okay, just like sound waves, the speed depends upon the medium. But unlike sound waves, it's backwards. Remember, with sound, it was more dense the faster it went. Well, here it is with light and the electromagnetic spectrum. The more dense the material, the slower the speed of light. What happens is light, it starts running into all those other molecules and slows down. So light travels fastest in a vacuum where there's nothing to get in its way. And c is the speed of light, 3.0 times 10 to the minus 8 meters per second. Okay, if you're using this in a calculation, please watch your units, right? Meters per second. So light doesn't require a medium. It's electromagnetic, which means basically you have a perpendicular electric wave and a magnetic wave, which is a whole nother lecture. But what happens with light and dense material, though, is it slows down. Just some vocabulary. If it's luminous, you give off light, like the sun, any of the stars. If it's illuminated, it reflects light, like the moon. Okay? The moon is illuminated. It reflects light back to Earth. A couple other words. Opaque. Opaque means light does not pass through. Okay? there's something transparent. If it's transparent, you can see the light will still come through. Only a little bit of light is absorbed or reflected, okay? So if it's transparent, a lot of the light is getting through. If it's opaque, none of the light is getting through. If some of the light passes through, it's called translucent, okay? The image will be distorted, okay, but some of the light is getting through. Now, with light and color, the colors of light are determined by the wavelength that an object reflects, okay? You see things because light reflects off of them. Objects appear to be white because all of the available colors of visible light are bouncing off of it. Okay? Your eye puts it all together and says, oh, that's white light. Okay? Well, now, what do those colors look like? Whoop, got ahead of myself. Objects appear to be black because they absorb all the colors of light. Okay? So black is the absence of light. We're going to get into mixing colors in a little bit, but you don't mix colors to get black. You take away colors, right? It's the total absence of color. You can also have a filter. A filter is a transparent material that absorbs all the colors except the one color or two colors that it transmits, whatever your filter is made of. Okay? And we'll get into that a little more as well. But just remember, black means that all colors have been absorbed, so you don't see anything. Nothing is reflected. Now, when we get to pigments, pigments act a little bit differently. Pigments are colored materials that absorb some colors and reflect others. Okay? You see a pair of blue jeans because you see blue. The other colors are absorbed. Does that make sense? You know, my tablecloth was red. You see the red, but the other colors are absorbed. Now, with light, we'll have, there are some primary colors of light, and light works differently than a lot of things. Colors are additive. That means they combine to form new colors. They don't take away colors, you add. The primary colors, red, green, and blue. Okay? Computer monitors, older computer monitors, basically those big ones, your parents probably still have one around. There's a little gun at the back that shoots little dots of red and green and blue and mixes all of those to figure out every other color. There are secondary colors of light, magenta, cyan, and yellow. So you mix the primary colors to get secondary colors. If you mix all of the primary colors, you get white light. But let's look at some of those. Okay? What do we got here? This is kind of like our primary colors. There's red, there's green, there's blue. Okay? Here's our yellow, here's our cyan, here's magenta. This is white. Okay? The red, green, and blue are primaries. When you mix primaries, you get secondaries. So the yellow, the cyan, and the magenta are secondary. Does that make sense? It's a little bit different for pigments, which are coming up in a little bit. And here they are. Pigments are subtractive. Okay, they combine to form black. The primary colors of pigment are magenta, cyan, and yellow. The secondary colors are your old red, green, and blue. It's just the opposite of light. You have to keep these in mind at all times. Okay? So pigments work a little bit differently. Okay? There's your cyan, there's your yellow, there's your magenta. That's an M. Okay? That'll give you your red, your green, and your blue, and then the black if all of them are mixed. Complementary colors are basically colors, and this will be for light. Complementary colors of light add up to produce white light. So you have one primary and one secondary. Remember that white light is the combination of all possible wavelengths. Okay? If you go to the pigment end of things, one primary pigment, and one secondary pigment, when mixed, produce black. Okay? So remember, these colors are going to be different for light and for pigments. Complementary light colors produce white. Complementary pigments produce black. So if we had some flashlights and put some filters on them, remember, we got red, we got green, we got blue. Okay? That's a B. Okay? From light, red and blue make magenta. Red and green make yellow. Blue and green make cyan, and when you mix them all, you get white. Pigments work differently. Remember, pigments work because the light is reflected off. Okay? So you have your magenta, your yellow, and your cyan. Okay? Cyan and yellow make green. Cyan and magenta make blue. Magenta and yellow make red. And if you mix them all, you get black. Okay? Polarized light is a little differently. A polarizing filter, like a polarized sunglasses, only allow waves through in one direction. Remember, I talked earlier, okay, electromagnetic waves are an alternating electric field and magnetic field, okay? But now what happens with a polarizing filter, which is most commonly used in sunglasses, okay? Unpolarized light here comes in going both ways, okay? If you have a pair of sunglasses on, you can take out one of those directions and filter the light by at least 50%. Now, how do these sunglasses work? Sunglasses, polarized sunglasses, work primarily because they work really well, because when light bounces off, say, the hood of your car, you know, when you're driving home and the sun is real low, or you're out on a boat or you're on a lake fishing at the end of the day, when that light gets low and reflects off a surface, it comes off polarized, and there's a whole lot of glare. But with a pair of polarized sunglasses, you can reduce that glare by eliminating that direction. Okay? So you might want to check your glasses when it says polarized. Is it polarized or is it just tinted? Polarized sunglasses take out one direction and reduce the amount of light getting to your eye. Wow, that's it. Okay. We'll talk to you later, guys.